And I would like to introduce the first speaker of this session is Dr. Selina Olthof. And Selina will tell us about metal oxide layers in perovskite solar cells. Selina, floor is yours.
Thank you so much, Julia, for the introduction. And yeah, as the title says, I want to talk today about metal oxide layers. And I want to tell you what they're good for in these perovskite solar stacks, but also what can be critical issues here. And I want to say right away that a lot of the work here was done together with Thomas Riedl, because he's really an expert in preparing very nice metal oxide layers. And so whenever you see some device stuff, it's usually made by him at the University of Wuppertal. Okay, so this is a conference about stability and degradation, so I want to start with some degradation examples. And we all know that MAPI films especially are very prone to destroy itself. So if you, for example, leave them out in ambient air, over a couple of days, MAPI films will turn yellow. You don't really need to wait a couple of days. If you just heat up your sample, you can really speed this up. And you can even do this in inert atmosphere. So even under nitrogen, if you heat it to sufficient temperature, it will degrade. So, I mean, this is quite well known. So due to air or heat, you can decompose your methammonium lead iodide into its constituents. And this is simply because it forms so easily, right? Whenever you have something that forms very easily, of course, it can dissociate very easily as well. And this is bad for our devices. And so we want to change this. And there are two possible solutions on the way to improving this. One is, of course, to make more stable perovskites. And we heard some people already talking about this, for example, making the cesium lead bromide perovskites, which are way more stable. The other method is to introduce barrier layers. So you can do a simple encapsulation to stop water from getting in. Or you can use these kind of 2D perovskites on top of your 3D perovskites, because it has been shown that they are hydrophobic, so they hinder the ingress of water as well. Or you can use metal oxide layers, as we already heard in the last talk. And I want to talk about this as well today, so how these metal oxide layers can be helpful in our devices. Okay, so Thomas Riedl does this work on these metal oxides, as I said, and he prepares them by atomic layer deposition. And he already showed that you can prepare very, very nice tin oxide layers, so very compact films with excellent vapor transmission rates. And they are very useful in devices because they are transparent and they're good electron transport materials. And so we wanted to employ these thin tin oxide films as barrier layers. We couldn't use them on their own. We had to use an additional azo layer, so this aluminum-doped zinc oxide, because they make a quite good electron extraction out of our device. And so down here you see three devices that were tested. One of them is a reference device. So here we have PSS, perovskite, PCBM, and a top contact. The next device is one where an azo film was added. So here we have just this azo layer. This is a Sol-Gel-produced film. It's a thick film, so 100 nanometers, but it is not compact, right? It has some holes, it has inhomogeneities. So we want to compare how this works when we compare it to one where we add on top of the azo layer this very dense tin oxide film, 20 nanometers, quite thin. And compare them with their stability and humidity and under elevated temperature. This is an IV characteristic of these devices, so they all look kind of the same, independent of the device stack. We get about 12 or 13%, so it's decent efficiency for these kind of stacks, and no hysteresis, as it's quite normal on these PDOT, as we already heard. But they are very different in their stability behavior. So if you look at the reference device here in green, it dies within a measurement. So these are all stored in air at room temperature and 50% humidity. The device with azo lived a little bit longer, but it as well died within about 50 hours. But the device with the double layer, so the azo and tin oxide layer, you can see here, it stayed a constant efficiency over the measurement time, which was about 400 hours here. So this double layer apparently really makes our devices very stable. And so we wanted to investigate what's going on for the azo film and what is better in this case of this double layer. And to look how the degradation could be happening, we looked at XRD. And what you see up here is an XRD measurement of the degraded azo-containing device. right? The one that died very quickly. And this is a measurement done after 7 days of storage in air. And what you surprisingly see is that it really looks like perovskite. So we do not see the lead iodide peak appearing, which we would have expected. If you really zoom into the area between 12 and 13 degrees, where you usually find the lead iodide peak, you find a tiny peak, but it's the same before degradation and after degradation. So no significant amount of lead iodide appeared, and this is really surprising because the device died, right? Something must have happened. And in order to find out what happened, we did XPS measurements as well, looking at the film composition. I'm sorry for the image here. The projector doesn't really like it. So you see survey scans of the azo-containing device and the double layer containing device. And we have here, you really don't see it, these peaks here come from silver. This one is a tin peak, oxygen peak, again, silver peaks, and so on. So all of this, just what we expect to have in these devices. But there's quite some difference after degradation. So after degradation, we have this new feature here appearing, which wasn't there before. And this is iodine. So after 7 days of storage in air, in the azo-containing device, we see a significant amount of iodine on the surface. This is not really the case for the double layer. We see a tiny amount, but not really relevant. And what happens here, you can see very nicely if you compare the SEM images of these surfaces, again, after degradation for 7 days. So this is an SEM image of the double layer device, which did not degrade practically, and it looks nice, nothing suspicious. But in the case of the azo interlayer alone, we see this appearance of many holes in the film. And if you zoom in, you really see that there's a hole, and around the hole somehow something happened, right? Something chemically changed, structurally changed the perovskite film. So we have a spotlight degradation in this azo device. And so what we think is happening here, if we have this double layer, it's really a dense film. The water cannot ingress into the sample, so it cannot reach the perovskite down here, and so the sample, even if you expose it to air, remains intact. But if you only have this azo layer, as I said, it's a sol gel process, so we have some remaining holes in there. Water can get through, can reach the perovskite film, and it dissociates the perovskite, and some iodine-containing species migrate to the surface, and corrode the silver top contact. And this is what leads to the device failure. It can't be very much that's coming out here because we don't see that iodide appearing. So it must really be tiny amounts that can already really lead to a destruction of our silver top contact. Okay, so in this first example, I showed you that we can help against extrinsic degradation using this dense tin oxide film. But what about intrinsic degradation? I mean, intrinsic is way more critical because you can always encapsulate and somehow make sure that your device doesn't see water or air. But if your active material itself decomposes, this is a more significant problem that has to be addressed. So here we compared as well, again, this azo-containing device with the double metal oxide layer. And here you see, again, quite a difference. So the azo-containing device dies within 400 hours. The double layer device doesn't die during the measurement time, so 1,000 hours, it was stable. Now, if we look at the XRD measurement, we indeed see lead iodide appearing in the azo cell, so the degradation mechanism is totally different here. We have lead iodide forming, and in the double layer cell, which did not degrade as a device, we don't see the lead iodide. We didn't expect to see the lead iodide. It just stays intact. Down here in the XPS measurements, so this is again fresh device and age device of these both stacks, you don't see the iodide appearing. So again, tells us very different degradation process. No iodine on the surface. And yeah, there's no iodine on the surface also leads to the fact that we do not see these pinholes with the surrounding weird changes to the metal contact either. So what we think what's happening here, if you only have this azo device and you start heating your sample, then your perovskite layer decomposes. So you form lead iodide and you form this methylammonium iodide and methylammonium and so on. And these components can leave through the PCBM, through the azo, out of the device. But intriguingly now, they don't react with the silver. So somehow water has to be present to make this reaction with the silver. And in the case of the double layer, which is, as I said before, very dense, these dissociation products, so the MEI and the MA and so on, they are trapped inside the device. They cannot leave the device. So what we think is happening, perovskite decomposes, but it reforms again, because all the components have to remain in the sac. And this means that such an approach of integrating barrier layers really can help against both extrinsic and intrinsic instability. And of course, if it would be even more advantageous to add another barrier layer underneath the perovskite, so this is ongoing work, of course. All right, so far I showed you good effects of a metal oxide layer that was far removed from the perovskite, so not in contact with the perovskite. But if you have a metal oxide adjacent to your perovskite layer, then several things can happen. So good things can happen. So this is a paper from the Lausanne group who showed if you change from titanium oxide to tin oxide, you can improve your device performance, right? This is just changes in energetic alignment and charge extraction efficiency. You can change morphology. So this is an example from my lab where we looked at the growth of perovskite in indium tin oxide and molybdenum oxide, and you can see how the crystal size severely changes when you change the substrate. So film growth is affected. And this isn't very impressive. Well, not on this projector impressive, but anywho, example that it can really change the degradation of your film. So here what this group around Cheng et al. Did was preparing MAPI films on top of zinc oxide. And if you prepare it fresh, it looks okayish black, even though you have quite some lead iodide in there. And then you anneal it very moderately at 60 degrees or so for 30 minutes, and this is supposed to be totally yellow. So this turns yellow at a temperature that is usually stable on titanium oxide and on any other substrate. So something must be happening at this interface that really triggers the decomposition of the whole film. So we wanted to look at these interfaces and see what's going on there. And I did not only choose metal oxides, so I had these two metal oxides here, molyoxide and ITO, and also P.PSS and PIA, because I wanted to cover a wide range of work functions in this study. And since I usually do photoelectron spectroscopy, this is what we did. So I incrementally evaporated the MAPI film on top. And after each evaporation step, I looked with XPS and UPS at the density of states and at the film composition. And I don't want to talk much about the UPS measurements and the energetic alignment. I just want to briefly show it here. So you get these interface dipole and band bending and so on. So these are quite complex interfaces if you look at the energetic alignment. But more interesting today, I think, for you is what is happening to the film composition at the interface. So what you see down here are XPS measurements of thick perovskite films. So after I put down 200 nanometers on 4 different substrates, right? The PIA, the ITO, the P. the moly oxide. And these are the carbon peaks. These are the nitrogen peaks, iodine peaks, lead peaks. So they look all the same on all 4 substrates, and this you would expect. These are thick films. They are not supposed to look any different on the different substrates. But if you look at the 3 nanometer deposited films, they look very different. So thin layers on these different substrates, very different. So you can see the intensity of, for example, of the carbon peaks are different, and you see new states appearing that were not there before, and they're not supposed to be there. So different chemical environment means different species sitting on the surface. And in order to explain to you what's happening, I made a little comic, so to say. So first look at the at the PIA sample, and the P. sample is doing almost the same thing. So when we start evaporating our 2 precursors to form the perovskite, we do get perovskite. So I can tell from the position of the peaks and from the area of the peaks that about 1/3 of the film is perovskite. Then we do get a different bond for the lead, so we know we have some lead oxide on the surface. We do have too much iodine, carbon and nitrogen, so we know we have methyl ammonium iodide in excess on the surface. We do have this additional nitrogen peak, more neutral, and an additional carbon peak, more neutral. So we know that we have something like methyl, amine, ammonium, hydrocarbons, and so on. So we know that the MEI must be partially dissociating, and we find dissociation products on the surface. overall, we can say on these two organic surfaces, the perovskite forms quite nicely, but about a third of it at 3 nanometer deposition. The story is very different on the metal oxides. So if you look at the indium tin oxide surface and we start evaporating, what we see is a purely more neutral carbon state. This one over here is missing. So we only have hydrocarbons and methyl iodide. So we see this more neutral iodide species. We are missing nitrogen. I do not see any of the nitrogen I put down. I maybe see a little bit of a peak at higher binding energy, so there might be some surface oxygen bond. So all of the methylammonium iodide dissociates, and this must be triggered by the metal oxide. I do not see enough lead. So in the case of ITO, you see it's much less lead compared to the two organic substrates. And on moly oxide, it's hard to see at all. So somehow I'm losing lead, which is very surprising for being such a heavy metal. So we have to have a volatile lead compound forming on the surface. And the only one you can think of is tetramethyl lead. So we think that the dissociation of the MEI leads to a reaction with the lead iodide forming this tetramethyl lead. We have some lead oxide, lead iodide, and some additional iodide bonds. So this is what this interface looks like. So it has no perovskite there. And you need to form this kind of buffer layer to really remove contact to this interface before the perovskite can start forming. So this is two very detrimental examples. We looked at titanium oxide as well, which I will not show today because it hasn't been published yet. But titanium oxide behaves very much like tin oxide. So this is what I can show you, and this has been published. So this is, again, work I did together with Thomas Riedel, who was interested in this interface between tin oxide and perovskite. So now it's the same ALD processed tin oxide layer, but at the bottom contact between indium tin oxide and perovskite. So again, a MAPI film. And what he observed was that when he changes the preparation conditions of this tin oxide film, then he significantly changes the efficiency of the solar cells, right? So all of these were prepared with tin oxide, but either by an ozone treatment in the ALD process, a plasma treatment, or a water treatment. And you can see efficiency changes and the hysteresis behavior changes. And he wanted to know what's going on there. So I looked at these different interfaces with UPS and as well as XPS, and looked at the energetic alignment and the composition. And this is the UPS measurements, the valence band and the vacuum level cutoff of the pure tin oxide layers. This is not very interesting, slight changes in work functions, but no big differences. When we put down a thin MAPI film, and this time this was solution processed, right? The last examples, it was always evaporated. Now we managed to make very thin, so less than 10 nanometer thick MAPI films by solution. And these are the valence band density of states of these 3 MAPI films on the 3 differently prepared tin oxide layers. And you can see they all look very similar. They're slightly shifted in energy, so something changes with respect to the extraction layers. But what is weird is that this does not look like perovskite. This looks like lead iodide again. So the black curve here that just showed up, this is how lead iodide looks like in UPS, and you can see this is just the same. And we did XPS measurements as well that I'm not showing now, but here again we are missing nitrogen, we are missing carbon, so the MEI fully dissociates and the MEI leaves the surface, even in the solution processing, and all we have left is lead iodide. Okay, so we have on top of these 3 different tin oxide layers, we get a layer of lead iodide. And then if we keep preparing thicker films, so 20 nanometers or thicker, then the density of state changes, and it now looks like perovskite. So after about 20 nanometers, you really have your perovskite film. And down here you see the energetic alignment. It's probably too small from the back, but you can just check the paper. This lead iodide layer is a charge extraction barrier. So this plays a significant role. And in the case of the ozone-treated tin oxide, it just happens to be, the lead iodide happens to be aligned with the tin oxide valence band. And so it's the least extraction barrier of all 3 cases, which is the reason why this is the best solar cell performance. Okay, so I hope I showed you that metal oxide can be very useful as charge extraction barriers, as gas penetration barriers in both directions, so coming in and coming out. So it really stabilizes these perovskite films. But if you are adjacent to one of these metal oxides with your perovskite film, you can really have significant chemical interaction and degradation. And these interlayers will certainly play a role in your device performance. And this is a reason why you never saw probably a proper device made on ITO or moly oxide, because you just have these very strong reactions. And it seems only to be possible to really make devices on these layers that make the lead iodide interlayer. And this is tin oxide, this is titanium oxide, and probably also the nickel oxide. Yeah. And with this, I want to thank, of course, Thomas Riedel for a lot of the good device work he did, and Kai Brinkmann made these lifetime device, Ting Hu made these tin oxide devices, and some people from the University of Cologne funding, and you for your attention.
Very interesting talk, but because of the time limit, maybe I can allow 2 questions. Yeah, I saw the 2 ladies and.
Very interesting work. What happens if you double the layer of AZO rather than adding tin oxide? Have you looked at that? Like, just keep the same thickness as if you have 2 double layers, but you have AZO. Have you tried that?
Without the AZO, you mean?
No, without tin oxide. Yeah, so rather than using tin oxide, tin oxide AZO, just double the layer of AZO. Do you get the same effect?
We have not tried. I don't think so, because with the solution processing, it will never be fully dense. So you really need this dense tin
even when
oxide.
you increase the thickness?
Is my feeling.
No,
I'm not
usually
sure.
when you increase the thickness, you reduce these problems. And why 50% humidity for your stability measurement? That's not typical.
That was the aging
humidity.
clause.
The moisture usually is 85%.
Yeah.
It's not 50%.
Yeah, I don't know why their setup was like this.
Yeah, that's atypical.
Yeah.
The last question is just a suggestion. If you can probe the surface using IR spectroscopy,
yes.
you can really determine what's on the surface.
Yes, we really wanted to do this, and we had somebody in Cologne who was kind of able, but it's very difficult for these thin films, and without any air exposure, we failed. But it's certainly on my mind.
Yeah, I really like the approach. Oh, stand up. Yeah, very nice approach, because it gives an idea of what's happening on the surface. I would argue that it's actually the MAPI that's causing you all the problems and not the metal oxides. Because if you switch to double cations and mixed anions, you will see that you have much, much more stable films. So you can actually make other types of perovskites on zinc oxide with no problems at all. I mean, no problems at all in the realm of perovskites, right? So have you looked at these mixed halides?
So first of all, I totally agree. The MAPI has a problem with the metal oxides. It just triggers a reaction there. We have not looked at other ones, but clearly looking at literature, formamidinium does not seem to make the same. And I think because maybe this tetramethyl lead, for example, is not forming with a formamidinium compound.
Okay, so some of these metal oxide surfaces are known for their self-cleaning properties because they use part of the UV light to trigger photochemical reactions.
Yeah.
So I guess this might be related to the fact that they're very reactive and may damage the film. You think this could be correct? Would you?
Well,
thank you.
It could partly. So the titanium oxide is really known for this, but the tin oxide is not. And they behave kind of similar. But certainly these are, especially the hydroxyl groups on these surfaces, I mean, they are extremely reactive, and these probably trigger all of this. Yeah, and we see that it gets reduced up on these reactions, the substrates.
I think we need to go further, and let's thanks Selina again.